During the last lecture, we talked about cryptography, and we showed that if we decided to encrypt the messages between two different entities, we can use cryptography algorithms, and we said that we can use cryptographic with symmetric keys algorithms, or we can use asymmetric keys algorithms with asymmetric keys. And we said that if we use our encryption methods with symmetric keys, those methods are faster, they need lower power with respect to the asymmetric keys, but in the algorithm with symmetric keys, we have a big problem: how we can share the key safely. Okay, but in the second group, the encryption algorithms with asymmetric keys, we use two different keys, one public key and another one is a private key. I can publish my public key, and if someone else tries to send me something, he or she can encrypt the message by my public key, and after that the message would be decrypted only by my private key. My private key is in my pocket. So the asymmetric key algorithms are more powerful, but they are using, as we saw in RSA. They are using more powers. They have more calculations. So we need something new. And finally, we said that okay, we can start with an asymmetric key algorithm, and then over that algorithm we can share the shared key of a symmetric key algorithm, and after that we can work with the symmetric key algorithm. Okay. Today we want to continue our talk, and we want to talk about authentication. Let's get back to the our example, Alice and Bob, two lovers. Okay. Alice tried to send a message to Bob, but firstly, Alice should introduce herself. Oh, Bob, I am Alice. So, one main question: how Bob can identify that this is real Alice? We are talking about a virtual world. We're talking about internet. Someone send a message to me. Okay, I'm Alice. Really? Are you Alice? How can I understand? How can I prove that you are Alice? Let me know. How can I prove you are Alice? I need an authentication mechanism. Maybe someone else, maybe Trudy, send that message to me. Oh, I am Alice. Hey, I don't know who sent that message. So I need a protocol, I need a mechanism to prove that the real Alice sends the message to me. Okay? So, when we talk about authentication, we are looking for a proving mechanism to prove the identity of the other side. In the simplest form, just I'm asking, who are you? And the other side will answer, I am Alice. This is the simplest form. Okay, he's Alice. I asked her, and he said that I am Alice. So he is authenticated. From one point of view, this is Alice. Because she told me I am Alice. Okay? But this scenario is not enough. And maybe Trudy send me that message. Look at this one. Here, the Trudy send this message. Okay, I am Alice. Do the cartoon here in the right corner of this slide. You can see that instead of Alice, her dog, for example, send me this message. I am Alice. This is a dog. I don't know who is he. Okay, I cannot see Alice. Just I receive a message. But I am Alice. So this strategy, Alice says that I am Alice, is not enough, and we need something else. Okay. Let me try another strategy. Alice would send a message for me. I am Alice, and to prove her identity, he sent me his IP address too. Okay, I am Alice. This is my IP address. Is it enough? No. Why? Because Trudy is here. If Trudy sniffs this packet here, if Trudy sniffs this packet, he or she can send this message to me, to Bob. For example, I'm Bob. Okay. The Trudy can sniff this message and resend this packet to me. Okay, I am Alice, and this is my IP address. It's message. That's I write. That's the Trudy writes the IP address, the Alice's IP address. It's simple. We call it a packet spoofing attack. The Trudy sniff Alice's packets, okay, and then after that, the Trudy resend those messages, or the Trudy creates similar messages with similar identities, and then he or she send those messages to Bob. I am Alice, and this is my IP address. So again, this scenario can be failed. Let me try another strategy. I am Alice, and this is my IP address, and this is my password. Alice has its own password. To prove that she is Alice, he sends her IP address, her message, and her password to Bob. And Bob said, okay, I know that you are Alice. Because, for example, because of that IP address. I don't know, something like that. Okay. Again, this strategy is not enough. Because if the Trudy sniffs that packet, the Trudy can resend or replay or play back that message to Bob. Oh, I am Alice. This is my secret key, my password. And this is my IP address. And Bob would be satisfied. Why? Because he receives a message with Alice's password, with Alice's IP address. Okay? So, Trudy can use playback attacks. To break this communication, to hijack this communication. It's very simple. Okay, maybe someone says that, okay, Alice can encrypt her password. Here, Alice sends her password in plain text format without encryption. So maybe someone says that, okay, Alice can encrypt her message, her password, her secret key. And then she can send those messages to Bob, and Bob answer to Alice, would answer to Alice, okay? But it's not important. Even if you encrypt your password, nothing will be changed. Why? Because the Trudy, still the Trudy can play back, can use playback attacks. The Trudy can sniff packets and then resend or replay or play back those messages to Bob. Sometime else after that. So that encryption cannot solve my problem. The other strategy is this, the first strategy. Alice would say, I am Alice. Bob would say, oh, really? You are Alice? You are Alice? Okay. If you are Alice, you have our shared key. We have a shared key. I have a shared key with Alice. Alice has a copy of that key, and I have a copy too. So, Bob would say that, okay, if you are Alice, please encrypt this message for me. Bob will send a message to Alice. Okay, if you are Alice, encrypt this message to me. Because you have you have a copy of our shared key. So if Alice is the real Alice, she can encrypt the message, the received message from Bob. Bob can change this message sometime else, okay? And Alice, only Alice can know what's that shared key. And then she can encrypt the message, the received message from Bob with that shared key, and she will send it to Bob, and Bob can decrypt the message and check the received message with R. But we decrypt this encrypted message and the result, and then it can check the result with his sent message. Okay. Here we know that we have a shared key between Alice and Bob. Each of them has his or her own copy of the key, and using this simple strategy, they can authenticate the other side. But this strategy has a simple drawbacks. Yes, Yasser, I will answer your question. This is a simple strategy. And I'm saying that Alice and Bob, both of them, has a shared key. But at the end of this, at the bottom of this slide, you can see failures and drawbacks words. Why? The answer is simple. As we talked in the encryption in the last lecture, when we are using a shared key encryption strategy, the problem is how we can share that key safely, securely, because the key is unique. If someone hears that key or receives that key, he or she can encrypt or decrypt the messages. So this is a real problem. How I can share that keys? So we can say, okay, if you are worried about the shared key, okay, use an asynchronous cryptography or use public key and private key encryption strategies. Okay. Let me check this new one strategy. I am Alice. Bob would send the message R for Alice. Alice will return the encrypted message by her private key. Pay attention. This encrypted message is prepared using the private key of Alice. Look at this minus sign. It means that this key is the private key of Alice. The Alice's private key. Okay. So simply, Bob can ask the Alice, okay, send me your public key. Alice can send her public key. We talked about it in the last session. Always we publish the public key over the internet. There is something wrong here. We should omit this part here. Here. this part here. Omit this part here. Look at this one. The Alice receives this message, Mr. Message R. Then she sent an encrypted form of message R encrypted with her private key. Okay, this one here. This minus sign. This means that this key is a private key. And after that, the bot would ask for her public key. This public key is published over internet. Alice would send it. Why? Why bot is looks for this public key? Look at this here. In asymmetric cryptography algorithms, always, if I encrypt a message with one of those keys, only I can decrypt the result with the other key. Here, firstly, the message is encrypted with the private key, so to decrypt it, only we can use the public key here. So when Bob looks for this public key, he tries to decrypt the message here. He tries to decrypt this message, the encrypted message by Alice. Okay? Using this strategy, we can remove the risk of publishing a shared key or sending a shared key over internet, over an unsafe platform. Okay. In this slide, we have a specific phrase, nonce. But what is nonce? We should talk about it. We should talk about nonce. Okay. Is this strategy safe here? Is it enough? Is it complete? Yes or no? It's a good question. Let me show a man in the middle attack or a woman in the middle attack. What is this attack? In man in the middle or woman in the middle attack, a man or woman sits and passes the route between Alice and Bob. Between Alice and Bob. Get this one? This is Alice. This is Bob on the right side. And Trudy sits here. Between Alice and Bob. We called it man in the middle attack. So what's the problem? The problem is this. When Alice sends her message, "Oh, I am Alice," this message is sent to Trudy, not to Bob. In man in the middle attack, the Trudy will answer, "Okay, this is my message, encrypt it." The Alice will encrypt it by this one here, and then I'm asking the Alice for her public key, and she will send it to me. But here I can understand that the other side is Trudy. And at the same time, when Alice send me a message, "Okay, I am Alice," the Trudy will send a similar message to Bob, "I am Alice." And Bob said, "Okay, let me decrypt this message, encrypt this message." The Trudy would encrypt it, but with her or his key. Here, K of T, key of the Trudy. Okay, this one here. This one here. This is straightforward. This is simple. The Trudy sits between Alice and Bob, and he or she, the Trudy, will answer to the other side. She create a communication with Alice and creates another communication with Bob. After this authentication mechanism, Alice thinks that there is Bob in the other side, and Bob thinks that, okay, this is Alice in my communication. But we know that is not true. Okay? So we should be clear about this. Okay, please wait a minute. I will be back soon. Please wait. R is not key. R is a message. R is a message. Okay? K is the key. K is the key. If you can see here, if we put a minus sign over K, something like this here, a K with minus sign, it means that this is a private key. And if I put a plus sign over a K, over the K, it means that this is the public key. This is a public key. So K with a minus sign is a private key. K with a plus sign is a public key. Okay? Here, K of A means that this is the key, this is the Alice key. And K of T here means that this is through this key. This is through this key. T means Trudy. A means Alice. B means Bob. Okay? A is Alice. This key is Alice key, a private, and Alice's private key. Alice's public key. Trudy's private key. Trudy's public key. So minus means private, plus means public, and AT and other signs means name of the owner of that key. K of A means Alice is owner of that key. K of T means K with substitute of K, T means that Trudy is the owner of that key. Okay? Here, look at this one here. I'm looking about this one here. Or here. This is minus or plus. If I write K with a minus sign, I mean a public key. If I write a K with plus sign, I mean a public key. Is it okay? A here, A means Alice, T means owner is Trudy. Okay, let me talk about this one here. I said that Alice, the Bob, will send a message to Alice, and Alice should answer. Alice must answer or must return the message, but in an encrypted form. Here, Alice will send an encrypted form of message R. But one question, okay, if I know the Bob's message, so if I sniff the Bob's message and the encrypted form sent by Alice, and even the public key of Alice, can I break this mechanism? Maybe yes. Why? How can I encrypt this message? If Bob use a similar message here, and a static message R, Bob always use a static message R to send to Alice. So Trudy can sniff the messages and resend or replay or play back those messages. So Trudy can break this mechanism easily. What does it mean? It means that Bob have to change this message over the time. Bob must use a mechanism to change the message R along the time. Bob cannot reuse and resend a past message to Alice, because whenever, pay attention, whenever you resend a packet, a repeated packet over the internet, over the network, the attacker can break your security mechanism. This is the key principle to break a security mechanism. We must never send a message twice. We mustn't repeat the messages. If we repeat something, then the attacker can break the security mechanism. So Bob must not send a similar message as a static message to Alice. Bob must change that message over the time. But how? The answer is simple, using a nonce. But what is nonce? It's simple. It's a time tag. It's a timestamp. Okay? If you look on the date and time of your computer, you can see, for example, okay, today is December 4, 2020, and time now is 4:56 Tehran time, or 4:26 Baghdad time. Okay? And even I can talk about even seconds. For example, 4:56, 30 seconds. And now, if I repeat it, this is December 4, 2021, 4:57 and 1 second. If I repeat it, this is December 4, 2001, 4:57 with, for example, 10 seconds. Okay? Along the time, I can see that my time is increased. My time is changed. I'm looking for something like this. So, when we talk about nonce, it means that I'm looking for something related, not a number. It's a string. It's a big string, consists of different parts. It's not a single number. It's an yes, Hannah, yes. You can find nonce in blockchain, yes. Because of this. We are using nonce to change the state over the time. And that nonce wouldn't repeat again because the clock is going forward always. You cannot go back in dates. Okay? We cannot go back in dates, in time. We always go forward. So, simply we can prove that a nonce would never repeat in the history. So, when Bob sends the message R to Alice, he is using a nonce in his message. Then, if the truth is sits in the past between Alice and Bob, and sniff the packets, and then after, for example, after one hour, for example, if the router replay or play back the last messages to Bob, Okay, Trudy sniff those packets, and then the Trudy tries to resend those packets to Bob. Here, when Bob received this public key, and in the past he receives the message encrypted with the private key of Alice. So simply he tried to extract, to decrypt the message and retrieve the R. And then Bob would check the nonce. Now, if the nonce is old, simply Bob will drop it. Okay, Alice, your message is old, it's dead. Your message is dead. The time of this message is finished, is over. You know, using the nonce. Each nonce must reply in a short time. After that, for example, I think that my message should be returned in, for example, 3 seconds, 5 seconds, not more. So if the Trudy replied my message, for example, 10 minutes later, so its time is over. Okay, the time is announced is over. The time is passed. So Bob simply would drop the message, and if the real Alice sends this packet, we never accept that message. The real Alice must resend or redo these steps again. Again, she have to send his private message, I am Alice, and Bob would send another message to Alice, and then Alice should redo all of these steps. Maximum 5 seconds is a sample. I don't know. It depends on your case. Maybe a system accepts a wider range of time, a bigger interval. Maybe yes, maybe no. It depends. For example, if my system is placed in my network, the sender and receiver are in similar network, so we can decrease this time. For example, we can decrease it to 1 or 2 seconds. And if we are working over the internet, we can increase this time. This nonce strategy is very helpful. Is a helpful strategy. For example, when you are installing security tools in your car or in your home, using remotes to open the car's door, the doors of your car or the door of your home. Okay. In that remote, we are using a nonce strategy. If you don't use that nonce strategy, someone else can sniff for example, when I'm pushing the open door key. Okay, there's a key on my remote to open the door. Okay, when I push that key, the doors of my car will be open. Okay, if a Trudy is near to my car and he or she sniffs my messages, my remote messages, then simply the Trudy can sniff it and play back it to my car. The result is interesting. The doors of my car will be open. I'm not in my car, around my car at that time. But the Trudy simply can open my car, the doors of my car, just using a simple sniffer. So, in anti-theft systems, security systems in the cars or in homes, we have to use nouns strategy. Otherwise, someone else can come, a Trudy can come and steal my car or my home. Okay. Let me talk about something interesting: digital signature. In today's internet, mostly we are looking for a strategy to check the identity of the other side. For example, there is a remote web server over the internet, and I received a message from that remote server. How can I prove that this is the real server? I need a mechanism to verify. Okay, this is Alice or this is Bob. And that Alice and Bob can never forgivable her or his identity. So how can I prove this? For example, I receive a letter. Okay, for example, this letter comes to me, the Dr. Rahman, for example, send a message to me. Okay, how can I prove that Dr. Rahman is sending this message to me? Or, for example, the dean of the university send a message to me, send a letter to me. How can I prove that this is Dr. Hamidi's message to me, dean of the university? How can I prove it? I'm looking for a signature of Dr. Hamid's signature. Oh, okay, I'm looking for a signature. Or I'm looking for a signature for the Dr. Rahmani's signature. Okay, Dr. Rahmani signs this letter. Can we have a similar strategy in digital world? Can we have something similar in all digital world, especially when I try to send a request, for example, to buy something? Yes, I'm looking for a proof system, proving the identity of the other side. Okay? The identity should be verifiable and non-forgeable. No one can say, okay, it's not me. If I have a letter, I can show the sign. Okay? Is it your sign? Your signature? Yes or no? You send me this letter, and this is your sign, your signature, here, at the bottom of this letter. This is your signature. So you send me this message. And he, the man or the woman on the other side, he or she cannot say, oh no, this is not my letter. Yes, this is his letter or her letter. Why? Because of that signature at the bottom of the letter. That signature verifies his or her identity. I'm looking for something like that in digital world. So we call it digital signature. I'm looking for a digital signature. It means that I'm looking for a strategy that when Bobs send a message to Alice, for example, oh dear Alice, oh how I have miss you, I think you are all the time, and something like that. And Bob signs this message. But how? How can prove that this message comes from Bob's side? With the strategies that we learned until now, I can say that, okay, if we are looking to prove that this message signed by Bob, it's simple. How? Okay, Bob, if you are the real Bob, encrypt your message with your private key. The Bob should encrypt his message with his private key. And then, look at this one here. And then send the message. The Bob should send his message, say M, to Alice plus message plus the encrypted message, encrypted with his private key. The encrypted text with his private key. And here, look at this one here. This is the main text of the message. And finally, that encrypted text. We are using that encrypted text as a signature. We are putting it on the bottom of this letter. And this message is sent to Alice. But why? Why this one works? It's simple. Again, it's simple. Why? Why it's simple? How can I prove that this message comes from Bob's side? Very easy. It's very easy. How? I know that the Bob's public key is published over the internet. Always. Always. The public keys are published over the internet. And now I'm asking Bob to sign this message with his private key. So Alice can receive the Bob's public key from the internet. And now Alice receives an encrypted message from Bob's side, encrypted with the private key. So simply, we talked in the last lecture. If you encrypt a message with one of those keys, only you can decrypt that message, that encrypted message, with the other key. So if the real Bob signs this message, encrypt this message with his private key, simply I can decrypt that message with the Bob's public key. This key is over the internet, so I can download it and decrypt the message. After decryption, if I receive a similar text with this one here, I said that I should send the plain text plus the encrypted text. So here I have a plain text and I have another plain text extracted from this encrypted text. So simply Alice should compare those to those texts. One text comes from the Bob side and the other text is extracted from the encrypted message. If the body of those texts are similar, we can prove that, okay, Bob signed this message. But if they are not similar, something is wrong. This is not Bob. If they are not similar, something is wrong. This is not Bob. Why? Because I couldn't decrypt the message. After decryption, I can see that result is not similar to the main text. So Bob signs message M. No one else can sign the message with that form, in that form, because Bob signs the message with his private key. So no one else can sign the message M in that. And this means that if Bob signed the message M, he does not sign the message M prime. How we can use this digital signature? Simply, for example, for example, I receive a box. Okay, you are buying this box. Please pay me, for example, $100 for this. Me, I bought nothing. I wasn't. It's not my order. No, you bought this. This is your address. This is your phone number. You bought this. You have to pay it. No, I never paid for this. I don't like it. I have no money to pay for this. So we have to go to court. Okay, gentlemen. These guys say that he never ordered these tools, for example. And I have this order and we don't want to pay for that. At that time, the court will receive my public key, and the other side, for example, Alice can send the message and the encrypted message, the encrypted version of the message. Alice would take those items to the court, and I will send my public key to court. If the court can decrypt my message correctly, it means that I make that order. I bought something, and the court will enforce me to pay for that order. But if the court does not decrypt the message, the court will say, okay, this is a fake order. This is not Bob's order. So everything is finished for me. This is a fake order and It's not my order. We call it non-repudiation. It means that the court can prove that this is the Bob's message, yes or no. No one can cheat here. It's simple. No one can cheat here. If Bob signs it with his private key, so the court can decrypt it with the Bob's public key. Okay. Okay. So, one main question. I'm looking for an encryption here. Something encrypted with the Bob's private key. Maybe something happens wrong here in this case. Okay. And also, if I encrypt a text, a large text, if I encrypt it, for example, I have a text, I have a 100 kilobyte text, I'm encrypted. So the result is still 100 kilobyte. So I have to send 200 kilobytes, 100 kilobytes for the real message and 100 kilobytes for the encrypted form of the message. Okay. Can I use something else? Use something smaller than this. Use something very special, very complicated, but simple, small, in a small form. Something like footprint. Look at your fingers. You have some fingerprints in each of your fingers. You have different fingerprints. None of your fingers have similar fingerprints. Can I put something like fingerprint, digital fingerprint in my message? If I do that, I can find a simpler form. To put at the end of my message. So I'm looking for a fixed length, easy to compute digital fingerprint. Because I know that if I use public key and private key for line messages, I have to pay too many computational, for example, computations for time, for space, for computation, power. I have to pay too many. I'm looking for something simpler, something like a digital fingerprint. Have we something like this? Yes. The answer is yes. We can use a hash function. If I put a large message M into a hash function H, I can receive a simple form of hash, H of M. The output is a fixed length, easy to compute message. We call it hash or a message digest. The properties of a hash function is that here we put a large, too many characters, a large file with too many characters into a hash function, and the result of that hash function is fixed. So the hash function is many to one. We are putting too many bytes into the hash function, and the result is, for example, 1 byte, 2 byte, or something like that. Okay? It depends on your situation. And the result has a fixed width, fixed size. We are looking for fingerprints. So, yes, honey, that's correct. The hash function is one-way. Is a one-way function. It means that if I put a large message m into a hash function and receive hash function of n, I cannot put it back into the hash function to receive the message, the original message. I cannot do this. This is a one-way function. One way. I cannot go back. And this capability yes, exactly. This capability is very important in security tools. For example, in Windows, when I create a user in Windows and putting a password, okay, and creating a password for a user, the Windows will hash my password. That password would save in a special file. Next time when I try to enter my password, again the Windows would encrypt, would hash my new entered password, and then the Windows would compare the hash of the new password with the hash of the old password. I have hash, old hash, in a special file in Windows. My new entered password would be hashed, and then the Windows would compare the new hash with the old one. If they are similar, then I'm authenticated. I can enter into the Windows. Otherwise, oh, sorry, you cannot enter. Your password is wrong. We use this strategy in different cases. We can use internet checksum, but internet checksum is the checksum is a poor hash function. Why? Because if I change, for example, you get one here, 1 and 9. If I change their positions, I can see here that the result is simple. The result is the same. I'm changing the message, but the result does not change. So the checksum is poor. Is a poor hash function, and I should look for something else, for something strong, more stronger than this. Okay. Here, so I'm using a strong hash function. So when someone tries to send a message, firstly, he should use a hash function to create his hash, and then that hash would be encrypted by the private key. So we send the message M plus the encrypted format of the hash, of the results of the hash function, encrypted by the private key. Okay? And we know that this hash value is simple, is short, with fixed size. So in the receiver, firstly, we should decrypt the hash function using the public key of Bob, and at the same time, we encrypt, we hash the received message by the hash function. This hash function is similar to this one here. We have a hash here and a decrypted hash here. So simply we should check them. If they are equal, the received message is correct. The received message has not changes during the pass along the internet, does not altered. If they are equal, it means that the message does not alter. Okay? This is the last slide for today. When we talk about hash function, in today's internet, we have two string format of hash function. One of them is MD5 hash function, which is based on RFC 1321. This hash function computes message digest with length of 128 bits in 4 steps, and this 128-bit message or a string is arbitrary and it's difficult to rehashing or deciphering here. The other strategy, which is common in today's internet, is SHA-1. This is a US standard, and in this standard, the message digest has 160-bit length. It's somewhat more stronger than MD5, but both of them are good options. You can use one of them to prove that your message does not alter. And again, the hash function, we cannot go back in the hash function. Maybe you find a strategy to recheck the results of the hash. Okay, but at that time you need to find too many samples and their hash functions. If you do that, then you can decrypt the hash digest and replace them. But you need too many samples and just compare those samples with the hash functions. You cannot decrypt those messages. Okay. Is there any question? Any question? Okay, I wish the best for you. Thank you and bye bye.